Hello, I'm Tegan,
I'm a board.
and we're representing Plano West Robotics today. We're going to be talking about game scheduling, which is a form of programming logic that helps your robot move more efficiently and more accurately in autonomous.
So first we're going to be talking about what game scheduling actually is and why you could ever use it. And then next we're going to talk about how you can implement it from FTC standpoint. And then we're going to be giving you guys a live demo. First we'll show you what the robot does without game scheduling. Then we'll show you what it does with game scheduling.
Okay, so first of all, let's talk about what game scheduling actually is. In essence, it's a nonlinear control system. So what does that mean? Normally, we're all used to having like your linear control systems, like mainly your PID controllers, right? And those are working really effectively for most teams right now, except we do run into a problem a lot in autonomous, and that is the fact that in real life, 99% of things are nonlinear. So everyone knows that feeling where you're running your autonomous and then some unforeseen variable happens and it doesn't work the way you expect it to. Obviously, we're never going to be able to incorporate every single variable inside of our code, but one way that we can circumvent that problem is by using a nonlinear control system such as game scheduling. So you can see here on the diagram that normally your linear control system is always going to be directly proportional to your measured error in some way. Nonlinear control systems, they work very similarly by using separate sets of linear control systems inside of your specific architecture that you set up, which we're going to talk more about later. So why would you use game scheduling? Well, first of all, it's familiar because as I said earlier, what you're doing is aggregating multiple linear controllers together into either like a model function, a step function, anything that you deem is going to be necessary. And secondly, it's really not that difficult to implement, and you can choose a wide variety of different techniques in order to best suit your purposes. So let's go into a technical overview of what game scheduling is. On the right, you can see we have a diagram of two different types of architectures. First, you have game scheduling, that's what people normally use. It's kind of like a step staircase. And the second one is continuous game scheduling, which is going to use mathematical models to get that continuous movement. Since it's not going to be 100% accurate to the real world, but it does its job enough, it's a heuristic. And it's a heuristic optimized for simple implementation because in FDC, oftentimes we don't have as much time as we need to work on every single aspect of our code. There are only two terms you need to know for game scheduling. They're fairly self-explanatory. I'm going to start from the bottom and work my way up. First, we have your scheduling variable, which is the input that the controller works around. You can have 1, 2, 3, as many scheduling variables as you need, but just know that the more scheduling variables you do have, the more tuning you'll have to do. It increases exponentially. Next, you have your gains, which is your output variables. And in our case, for this demo, it's just going to be our PID values.
All right, so now let's talk a little bit more about how you'd actually go about implementing it in FTC. So first, what you have to do is you have to choose your scheduling variable. So for us, that's going to be the height of our slide. And for you, could be anything that changes the functionality of your robot. So many FTC robots have like protruding arms or slides that go up, or just the general things that can change how your robot functions on the field. And any of those can be your scheduling variable. So then you find your design points. Your design point is just points at your scheduling variable that you want to tune your PID gains at. So for us, that'll be the bottom of our slide and the top of our slide. So bottom of our slide is 0 and the top is around 1000. That's just an example. You guys can do this for, let's say, the yaw of your robot, pitch, an arm that extends from it, really anything. And then what you do is at each design point, you tune the PID gains. So you just go to each one, you tune the gains at each point, and then after that, you have to choose an architecture. So we're going to be talking about 3 different types of architectures today. There's a simple switch, a linear switch, and a modeled switch. So as you can see here, the simple switch is at the very top, and you see how it just jumps down in steps, kind of. So some pros are that it's very easy to implement and it takes a very little time to develop because essentially what it is just a bunch of if statements. And let's say if the scheduling variable is equal to the design point, then your PID gains are this. Else if the the scheduling variable is equal to your design point, another design point, then the PID gains are something else. And some problems with this is that it's not very optimal because these jumps, they can cause your robot to make very sudden changes or it can lead to oscillations. So let's say your scheduling variable, the value of it is hovering around the design point. So what that can lead to is some oscillations as it rapidly switches between the two different PID gains. So next up, we have the linear switch, which is essentially you just choosing your design points and linearly interpolating between them. So this can be optimized a lot more than the simple switch because you can control how far you want your line to go. And it's a lot smoother, so you don't have problems with oscillations or sudden changes. Also, some problems are that it can be a bit difficult to develop, or at least it's more difficult than the simple switch we have up there. Next, third one is the modeled switch. And what this is just a mathematical function where the scheduling variable is the input and your PID gains are the output. So this is going to be the most optimal solution if you can get it right. And because of that, it's somewhat more customizable because you can change a lot more about the function than you can with the scheduling with the simple switch and the linear switch. But some problems are that you might have to find a lot more design points to actually get the modeled switch to work the way you want. And along with that, it's kind of difficult to maintain because if you want to make a small change, you have to come up with a new function that you're using. And along with that, it also takes a lot more time to develop. So let's say you're in the very beginning of your season, you know what your robot's going to be like, and you have a lot of time. Then we would recommend that you go with a modeled switch. But if you're in the middle of the season and you want to start implementing this, you should probably go with a simple switch or a linear switch. Okay, so now let's do the live demo. Oh, whoops. So here's some example code that we have. So as you can see, this is a simple switch that we have up here. And this is doing is you have the scheduling variable and 150 are 100, the number is 100 and the number 150 are our design points. So if the scheduling variable is equal to 100, then we set our PID gains to a certain value. And otherwise, if it's the other design point, then we set it to a different value. And if it's none of those design points, then we set it to a different value. So yeah, let's go to the live demo.
Okay, I'm gonna have to figure out how to do this in one hand. But okay, so first of all, let's show what happens just when you have a normal quality controller that's only tuned to one part of your robot. So this is usually what most humans end up doing during the season. Your robot moves forward and your robot moves back, no problems whatsoever. But the issue that occurs is when you have the moving slide. After having the slide up, obviously your center of gravity is going to change, your mass is going to change, and as a result, your inertia. So that's going to result in some error. Yeah. So that's going to result in some error in how your robot behaves. So if I try to move the same distance with the same PID controller, you'll see that the robot wobbles back and forth a little bit. I don't know how accurate the camera is, but you can see that even when it moves back to, it's going to shift a little bit and probably go off by about a centimeter each time. And that builds up. So in your auto, that's not what you want. So if you implement game scheduling, I'm going to turn game scheduling on and move the slide back down. Then no matter what your robot does, I'm just doing before and after the robot side moves, but it also works if you're doing like multi-threading, if you have your slide moving while the robot's moving or any other position. if you have your robot move with your normal PID values and then you move your slide up, then when your robot moves back with game scheduling, you can see that it barely moves at all. I'm going to show this one more time with it facing the front because it did get a little bit off during that previous demo. But this is with game scheduling, and the robot is able to use the new PMT and PID values to move a lot more accurately.
And yeah, so as you can see, there is a large performance difference between when you use game scheduling and when you don't use game scheduling. So let's go to the next slide. You guys have any questions? Yeah. Well, assuming that Roadrunner lets you change your drivetrain PID values as the robot is moving, then yeah, you can use it. But if you have to set the PID values before the robot is moving and those PID values have to be the same, then you can't. You'll have to do a little bit more research on that. Yeah?
So the demo regarding the height of the slide has the schedule variable.
Yes, we are.
Yeah, so right now we just have encoders inside our slide loaders, and then we're using that as a scheduling variable using a simple switch of architecture.
I think we have a question from the chat. How would you find the most optimal function for a model switch?
Well, generally what you do is you find you have to choose a lot of design points. So for each design point you go in, you have to choose each one and find the games for that design point. So let's say you have 5 design points. You can't really make a function out of that. So if you want a function, you have to have a lot more design points that you can interpolate between. So you can use something like a spline or just regression to find that.
Oh, and there's also the option of using separate third-party libraries to run your interpreting function. Like I believe with NetBC also has interpret to if you want to check that. But the problem with a lot of those software is that it comes with the one as well. So if you're very like mathematically defined, obviously you can find your own function.
I don't think there's any more questions in the chat. Yeah, okay. Thank you, Plano West.